6.2, and we started building triangles in different quadrants. So 6.1 was all about learning definitions, right? Standard position angle, terminal arm, terminal point, creating triangles, and we were always doing it in quadrant 1. When we did it in quadrant 1, we always used SOHCAHTOA, which we reviewed, right? Sine, cos, and tan. Today's Monday. Thursday, we started doing that in every single quadrant, and it kind of built up to this big idea of something called the cast rule. And the cast rule was telling you where certain things were positive. For instance, if you had a triangle like 10, and you said it was equal to 1 over 2, that's positive 1/2. We remember that 10 is actually y over x. So if 10 was positive 1 over 2, we could have built it right here. 1 over 2. And that was normal for us. What wasn't normal for us was we could also build that triangle in quadrant 4, where 10 can be positive. We would build it there, where it would have been negative 1 over negative 2, but two negatives cancel each other to be a positive. Right? And the idea was cast rule always told you where the positive ratios could go. So for instance, if you had a positive sine ratio, it could be built in the all or in the sine. If you had a positive cos ratio, it could be built in the all or it could be built in the cos. Yep.
Well, is there a situation where you either get one triangle in 3 of the quadrants or like 1 in 20 quadrants, or is it always quadrants?
It'll always be 2. So that leads us into our next thing, which is you should be able to catch on through elimination, the process of elimination. Every triangle will be built in 2 quadrants when there's no restrictions given, which we'll get into in a little bit. But if I give you a positive sign, it's in 1 and 2. If I give you a negative sign, it's in 3 and 4. Right? There's always 2 situations for any triangle that gets built. We then did a little bit of practice on where things could be built. So for instance, you looked at sine. You already did this example in part 1. Sine is positive. You do cast. That means it's in the all and it's in the sine quadrants. So this triangle could be built in 1 and 2. If you had something like cos is negative, you would look at your cast law, which tells you where things are allowed to be positive, and then you use kind of some reverse thinking. So if cos is negative, that means it's not positive. That means it would have been in 2 and 3. Because it's negative, which means it's not where it's positive, which is C and A. Okay, that's what 6.2 was building up and leading to. And we haven't really done any questions that would actually be useful to us. So we're going to do a couple of those. We'll start with this one, which is pretty standard. They give you a point B. It's at 2, -5. So they gave you the point right here. That's point B, 2, -5. Sketch the angle. Well, it's been sketched for you. But it said it's in standard position. So where would that angle be that they want you to find? Standard position means you start from your x-axis and you go counterclockwise. That's theta. So the angle is actually not inside your triangle. Part B. Determine the distance from the origin to point B. That would be from here, the origin, to here, point B. They want you to find that distance. We have a name for that line. We call it R. We also have a formula for it, saying that R equals the square root of x squared plus y squared. The reason that works is it's just Pythagorean Theorem. So if you look at this triangle, this side would be 2, and this side would be -5. So those are the coordinates that got you to that point. We could use Pythagorean Theorem to solve that, or you could use your formula for r. Both would be legitimate ways of solving it. This would be r equals 2 squared 2 squared plus negative 5 squared. That would be r equals the square root of 29. That's the exact value from the origin to the point B. All right, C. Write the primary trig ratios of theta. The primary trig ratios of theta. We're going to start with sine. The primary trig ratio for that is opposite over hypotenuse. It's also y over r. Right, those two formulas. So you can use SOHCAHTOA to figure that out, or you could use the y over r formula. That means it's equal to negative 5 over root 29. That would be a half mark if this was written response. The reason it's a half mark is because that thing needs to be rationalized. You're not allowed to have square roots on the bottom. Right? That's unit 1 review. So multiply by root 29, top and bottom. Your final answer for this ratio is negative 5 root 29 over 20. That's your sine ratio. Okay, now we're going to do the cos ratio. The cos ratio was x over r, which we had learned in previous lessons. That would be 2 over root 29. When you rationalize that, it becomes 2 root 29 over 29. The last ratio would be tan. Tan is opposite over adjacent, or y over x. Negative 5 over 2. Again, you could use SOHCAHTOA, or you could use your y over x formula. Both would work. All right, now we're going to learn something important. It's part D. Determine the measure of theta to the nearest degree. They're talking about the standard position angle, theta. This big guy all the way around here. You can't calculate things that are outside of a triangle. What you can calculate is this little guy in here. And use that to calculate what the standard position angle would be. That makes sense, right? We would go 360 and then subtract off that little chunk. That would tell me my standard position angle theta. What's different is that we've never had triangles with negative ratios before. We've always been solving SOHCAHTOA with positive values. That's going to change things a little bit. So when you go to solve these, you could use sine, cos, or tan, just like normal. And you take your calculator, you make sure it's in degree mode, which I'm sure you are. And you're going to go second sine negative 5 root 29 divided by 29. If you use the sine ratio and you calculate your angle, it'll tell you that the angle is in radian mode. It'll tell you that the angle is negative 68 degrees, which makes 0 sense to us. A little bit, but we're talking about inside of a triangle right now, right? Not reverse standard position. which is actually why it is negative. But we're not going to worry about it. You're going to notice that this thing was negative 68 degrees in your calculator, which is not going to be useful for you. Because inside this triangle, that measure right there, not negative 68. That won't make sense. If you try using your cos ratio, and you put that in your calculator, second cos, and then you get 2 root 29 divided by 29, you get, yeah, I know, I used to go. Positive 68 degrees. If you do the tangent one, second tan, negative 5 over 2, that one's much easier, you again will get negative 68 degrees. Now, some people might just be like, well, just get rid of the negative and you got the right answer, which it works if you're in quadrant 4. If you're in quadrant 3, it's not going to work. So, for instance, triangles in quadrant 3, you'll get 2 bad answers and 1 good answer. In quadrant 2, you'll get 2 bad answers and 1 right answer. So it's going to be up to you to figure out which answer is always going to be the right answer. And it won't always be negatives. Sometimes you're going to get answers of like 130 degrees. And you're going to be like, logically, there's no way that was 130 degrees. Right? Because you're inside of a triangle. So to pick the right ratio when calculating angles, you're going to use the cast rule. Which triangle or which quadrant was our triangle in? It was in quadrant 4, which was the C1, which means you should use the cos ratio. Notice that the cos ratio is the one that gave us the positive 68. That means if you have a question that built a triangle in quadrant 3, you would use the tan ratio to get the proper angle inside the triangle. For question in quadrant 2, you would use the sine ratio to get the proper angle inside your triangle. That's the second use of the cast rule. The first use is where you build things. The second use is you use that ratio when calculating angles inside your triangle. Yeah. It'll always be a positive angle that's less than 90. That's how you know if it's a good answer or not. Right? If you have a number that is anything bigger than 90, it's not possible in this triangle, right? Like logically. If you have anything less than 0, not logical at all, because you're talking about inside of a triangle. So use the cast rule to pick the right ratio to use. That means 68 degrees is that guy in there. We still have to calculate theta. Theta was equal to 360 minus 68. So your standard position theta was actually 290 degrees.
So, what you calculate a weird angle, like negative or...
You'll never use the negative angle. No. The reason your calculator is giving you negatives and stuff like that is it doesn't know what quadrant you built your triangle in. And that's why it's kind of confused and does weird things. This one, it just puts negatives on it because then it's like, well, you must have been down here somewhere, and it tries to build it using standard position angles. But once you go to quadrant 2 or quadrant 3, your calculator will start spitting out things like 132 because it's trying to give you the standard position angle to the closest that it can, which is why it gives you weird numbers. Because it's trying to figure out where you're actually building a triangle. If you just use the proper ratio, it'll always give you the one you actually want inside your triangle. Yeah. Yeah. All right. You try it. So here's a question. It's almost identical. You're going to have to draw it and build it and calculate it from start to finish. So go ahead, see if you can figure out where this thing is and what the angle is equal to. Talk about this. So the rationalizing seems to be throwing people off, right? So to rationalize, you multiply by whatever the root sign on the bottom is. But before I do that, I like to simplify anything I can before I rationalize. It makes my numbers smaller, it makes it easier to work with. So I would take, for instance, this 4 and this 2, and I would divide both of them by 2. That's why I end up with negative 2 root 5. Then I multiply top and bottom by root 5, which becomes negative 2 root 5 over 5. If you did the other way around, you should have ended up with negative 4 root 5 over 10. And then you have to simplify your coefficients, right? The 4 and the 10 can both be divided by 2. No matter what way you choose to rationalize, you should get the same answer. All right, those are all up there. We're not sweating the rationalization too much, and it is something you need to be able to do and practice a little bit more. But the main purpose here is calculating the angle. So part D says determine the measure of theta to the nearest degree. Theta is this huge standard position right here. All we can calculate is inside triangles, right there. And the way we calculate that is by using our trig ratios. Jenica used the sine law, I used the cosine law, and we both got weird answers. So what did you get for sine? So she got negative 63 degrees when she used sine. I used cos, I got 117 degrees. And if you use tan, you get positive 63 degrees. Right? You got 3 different answers by using the 3 different ratios. One of them is accurate for telling you this inside angle. Negative 63 makes no sense for a reference angle, because reference angles are always positive. 117 makes no sense for a reference angle, because just looking at this, there's no way that's 117, right? It's got to be less than 90, which is what a reference angle is. The correct answer would be 63 degrees for that reference angle. How would you know that that was the correct answer? Yeah. Exactly. The CAST rule tells you which ratio you should use. When you're in quadrant 3, you use the tan ratio to calculate your reference angle. That's your way through it. Without having to calculate all 3 and then compare and logically eliminate, just use the CAST rule. If this little guy in there is 63 degrees, that means theta is equal to 180 plus 63 degrees. Your final answer should have been 243 degrees. How many people actually got that? Like, that's good. How many people got stuck with the rationalizing? That was a lot. Most people, that's where they got caught, right? On rationalizing and remembering how to do that. And that's okay. That's a long time ago, so it's just going to take some practice. If you didn't rationalize your answer, let's talk about that for a second. If the question was just what's theta, your calculator doesn't care if it's rationalized or not. Okay? So you could skip the rationalizing step to find out what theta is. You only rationalize if they're asking what the trig ratio is equal to. That's when you actually have to give a proper answer. Awesome. Okay. It's another type of question you guys can get. This is going to deal with our definitions a little bit. Also, we're going to learn a little bit about general solution, which we talked about on day 1 but didn't do much of. So it says a terminal arm is rotated through an angle theta in standard position. The terminal arm contains point -4 and -8. That point would be down here somewhere. That means my terminal arm next to it. Right. There. That's my terminal arm. It goes through this point. -4, -8. So one decimal place, find the value of, and then there's a whole bunch of things here. The first thing he says, R. R is the distance from the origin to the point. That's R right there. This is trig. Everything's a triangle. So to make this thing into a triangle, we go like that, and we use our X and our Y coordinates as the other 2 sides. Right? Everything's a triangle in this unit. We can then use those sides, use Pythagorean Theorem, or use your formula. R is equal to the square root of x squared plus y squared. When you do that, you should get R is equal to 4 squared would be 16, 8 squared is 64. That's the square root of 80. And that should simplify down to be 4 root 5. 16 divided into 80. I think. And it goes in 5 times. Square root of 16 turns into 4. Alright, B. The reference angle. Let me do this in green. The reference angle is measured how? Yes, but how? But you're ahead of it. Where's the reference angle on a question? From the terminal arm to the closest x-axis. That's the reference angle in green. Right? That's different than, say, the standard position angle. So when they just say calculate the reference angle, you need to know which one that is. That's the one inside the triangle. To calculate that, you're going to use SOHCAHTOA. Which ratio would you choose? Why would you use 10?
Because it's the one that's opposite.
Exactly. Using the CAST rule, it tells me in this quadrant, use 10. So I go second 10, opposite over adjacent, negative 8 over negative 4. And it should be, let's see, the same as the last one. 67? Is that what it was? 63? 63. Yeah, 63. It did, for whatever reason, say to 1 decimal place. So I guess we'll go 63.4. Normally with angles, remember, we don't use decimals, but it specifically said 1 decimal place, so we just kind of follow the rules. I guess for the radius, we should have technically calculated that as well. All right, part C. Find the angle in standard position. Now, what are they looking for? Close. You're going from here, just continuing on. But standard position is a definition. And that definition says from the positive x, counterclockwise, until you hit the terminal arm. So that is my standard position, zeta, which would be 180 plus the 63.4. So 243.4 degrees would be the angle in standard position. You can see, like, there's a lot of definitions, right? So it makes it hard. It's easy when I'm talking it through with you guys, probably. You're like, yeah, I remember that. But then to actually remember it on your own on a test is tricky. You have to know which angle you're calculating. And if this is multiple choice, I guarantee you that both these answers are there. Right? I know what a definition is for standard position. This is I don't know. This is I know. All right, D, a coterminal angle. That's a definition we haven't talked about in a while. What's a coterminal angle mean? Co would mean 2, right? So it's another standard position angle that would get you to the same terminal arm. I'm going to show you two coterminal angles. Okay? First coterminal angle would be if I went all the way here, which would be 243 degrees. But then I took that terminal arm and I just spun it one more time all the way around. So I added 360. And that would give you the same terminal arm. So that would be 603.4. That's a coterminal angle. Yeah.
So you could just build the general solution to find coterminal angle.
Yeah. Yeah. If you can build the general solution, you can build coterminal angles.
Is that not a realistic question? Because there's multiple, or is that the only one?
There's more than this, because I could then do another 360,
Yeah,
right?
so-
And then I would have 363.4, and now we're at 963.4. That technically would be the same spot. So for general solution, and I'm just going to go off for a little bit because we're going to loop back and probably answer some questions. So for general solution, that means if you take your standard position angle, 243.4, and you add 360 degrees n times, that would be your general solution, where n is an element of the integers, meaning that it is a positive whole number or a negative whole number. You can't have decimals. The reason you can't have decimals is because if I don't do a full 360 degrees, then I never actually got back to the terminal arm, right? That's why you have to have this little part. N is an element of I, or you can have N as an element of W for whole numbers. Okay, now I'm going to loop back to coterminal angle, because there's another one. And there's a lot, right? We just talked about the infinite amount, but there's another way to do it. So I'm going to show you what I mean. I'm going to get rid of that black one. Okay, and I'm going to build another coterminal angle. What I'm going to do is I'm going to do the standard position angle again. 234. And last time I did a 360 from there. But that 360 went counterclockwise. I could do that 360 counterclockwise and loop back around like that. So instead of adding 360, I could have subtracted 360 degrees to get a coterminal angle. That means my general solution has plus 360 or minus 360. And it would give me another angle that gets to that coterminal arm. To do that, I would go 243.4 minus 360. That means negative 116.6 degrees is another coterminal angle. It's just the negative version of it, going backwards. Remember, coterminal angles are just things that get you to this arm. So you could go forwards or backwards, and it would work. A little trippy, right? Most of the time we only deal with the positive versions of things. It's very possible that you get given a negative one too. General solution we don't do a lot of. I think you'll probably see maybe one question on it. Next year it becomes a bigger part of your life. Okay. 2 examples. And two good examples. Okay, so given that tan of alpha equals negative 5 over 12, determine the other primary trigonometric ratios of angle alpha. The first thing I need to do is build this triangle. Anytime I'm given a ratio, I should start building a triangle. Tangent is always giving you side y and side x. If it was cos, they would have been giving me x and r. If it's sine, they would have given me y and r. I'm going to draw it. I think that's a wise choice. When I draw this thing, I have negative 5 over 12. So that means my y was down 5 over 12. I'm going to build it right there. Down 5 over 12. Right? Negative 5 divided by 12. This point is I got to use looks at me. We're good? All right. What's wrong with that? It's not wrong. What's missing? The r value is missing. That's true. Something else is missing. I made an assumption in there somewhere. I assumed that that negative was with my y value. What if that negative had been with the 12 and the x value? Then I would have built my triangle up here at 5, negative 12. Remember, all triangles can be built in 2 spots. There's the second spot. You need both of them. Right? Because you don't know. You don't know if this was negative 5 or negative 12. It doesn't say in this question anywhere. It doesn't say the negative is with the 5. It doesn't say that you're in the 4th quadrant. It doesn't say any of that. You saw 10 was negative. You use the cast rule to figure out which 2 it could go in. Like, all I know is that 5 is y and 12 is x, but I don't know which one's negative. Right? Like, the x's are both still 12. But this is positive x 12, this is negative 12. And that's why it gets built in 2 spots. Now. No, and so, like, that's the thing. You remember, like, floating negatives? So the standard way to write things is to put the negative to the top, but that's because that's just the standard letting it float to the top. That doesn't mean that the y value was actually the negative value. It just means that's how we would write it properly. Every triangle has 2 spots to build it. That also means that my trig ratios are going to be a little bit different, depending on which quadrant you're in. So for a question like this, I have to have 2 solutions. I have to have, this is what happens if I'm in quadrant 2. This is what happens if I'm in quadrant 4. So I actually have to solve 4 other trig ratios. Or, sorry, 3 other trig ratios. 10's technically given to us, but we should still write it down. If I'm in quadrant 2, my sine ratio is y divided by r. That means it's going to be 5 divided by r. What's my r value? We don't know. How could we figure it out? Awesome. By using your formula, which is 5 squared plus negative 12 squared. I think it's equal to 13. Okay. Anybody calculate it? 13? 14? 13? The only reason I know is because it's a Pythagorean triple. 13, yeah. So that means the sine ratio is 5 over 13 in quadrant 2. The cos ratio in quadrant 2 would be negative 12 over 13. X over r. You then redo the question for quadrant 4. The r measure would still be the same thing. It would still be 13. It's just now your positive and negatives have swapped. So in quadrant 4, your sine ratio, color, is now negative 5 over 12. Pretty close to the same thing, just negative. The cos ratio in quadrant 4, 13. The cos ratio would be positive 12 over 13. Those would be your other trigonomic ratios. And it depends on which quadrant you're in. All right. Question B. Yeah. Yeah.
So is alpha on both of those?
Yeah, so alpha is this little guy in here. Alpha is the reference angle. Yeah. And that reference angle would be the same thing for those two. It's just the triangle flipped into a different quadrant. To the nearest degree, determine the possible values for alpha. Okay, you're going to have two situations again. You're going to have alpha. It does. Well, what they want you to do is find the standard position angles. Okay, so that's not very clear because they reused alpha. They should have called it something different. But it will be clear. They want you to find the standard position angles that would create these two scenarios. You're going to have one answer for quadrant 2. You're going to have another answer for quadrant 4. Because they have different standard position angles. To be able to figure out the standard position angles, you need to know what the reference angle was. Yeah.
Does that mean it's rotated 3 times?
That means you can only go around twice. Yeah. 360 and then 720. We're going to talk about that too. We're going to just find the standard position angles first. The standard position angle for quadrant 2 would be 180 minus whatever alpha was, right? 180 minus. The one for question 3 would have been 360 minus alpha. Right? That'd be all the way around minus that little chunk. So that's your quadrant 3 or quadrant 2. That's your quadrant 4. You got to figure out what alpha is. To figure what alpha is, let's do quadrant 2. Which ratio would I use to calculate the reference angle? I would use sine because of the CAS rule. Right? CAS, S is quadrant 2. If I go second sine, 5 divided by 13, I can figure out that alpha equals 22 points. Near 23. And it's 23 degrees for both triangles. They're the same reference angle. Because it is the same triangle, just in a different spot, right? That means my standard position angle for quadrant 2 would have been 180 minus 23. It would have been 157 degrees. My standard position for quadrant 4 would have been 360 minus 23, which would be 337. Letting people look at that for a second, see if they have any questions or if that makes sense. Do those standard position angles make sense? Yeah. I'm telling you, because that's worded poorly. Yeah, it would say the standard position angle. It would make it clear to you. All right, those are the standard position angles, assuming you only ever did one rotation around, right? But there's a coterminal angle to 157. Remember, I could go to 157 and then do a full 360 and get the same angle, right? Pardon? I could for the other one too. Yeah, let me do both. So I could go 157 and then do an extra spin all the way around. That means that 517 is another answer for standard position angle. That's all the way around to 157 plus a full 360. I could do another 360 degrees again. So if I go plus 360, I get 877. That's where this part comes important. This part says that the angle has to be in between 0 and 720. My third coterminal angle of 877 does not fit into those restrictions. Therefore, for quadrant 2, the only answers are 157 and 517. It also means I can't go backwards, right? So if I did 157 minus 360, I wouldn't be in between 0 and 720. So you have to have general solutions or coterminal angles that fit in your restrictions. No.
If there wasn't any restrictions, let's say on a test applies to the future angle?
So if there wasn't any restrictions, that's when your answer would have to be the general solution. Yeah, but they would typically just ask you for the smallest one.
So if I put like the biggest angle I could think of,
Yeah, that would work.
could you figure it out?
I'd figure it out, yeah. Yeah, it's pretty easy to figure out because you just go minus whatever the actual center position is and then divide by 360. And if I get a whole number, then you're right. If I don't get a whole number, then you're wrong. Okay, quadrant 4. I want you to write down what the other answer would be because there's two that work. So what's the other angle for quadrant 4? That would be standard position. Anybody have it? 697. You just add another 360 to it. So those restrictions are going to start to become an important part of your life because it tells you how many times you can have your standard position rotate. Great, I think there should be a practice one. Perfect. I want you guys to try this practice one on your own. Full answer, so both triangles, both quadrants, all the way through. On this question, it should be -4 over 5. Like that. The reason being is it's y over r. Your hypotenuse can't be smaller than your y value. That shouldn't be a 3. Okay, now try the question. I've got some people stuck on Pythagorean Theorem to find the x value. So if you use Pythagorean Theorem to find x or y, then it's the square root of r squared minus whatever the other one is. So that would be your formula to find your x value for those things. And then you'd have to be able to understand that you could build to the left, so it's -3, and to the right would be +3. That would just be helping people out to keep them going. Doing this question, the first thing I have to do is draw it. Right? So I have sine as negative and then 4 over 5. The first thing that you probably want to know is that sine is equal to y over r. R is always positive. Always, right? It's the definition of r. So that means that it had to be -4 as my y value, and r was +5. There's two spots that can be built, quadrant 3 and quadrant 4. That's based off of understanding that r is always positive, which we did in 6.1. From there, I need to calculate the x value for those triangles. To do that, I do Pythagorean Theorem. Right? When I do Pythagorean Theorem, I get that x is 3. I also know that if I built it to the left, it would just be -3. So that's where my two triangles came from. I then wrote out all the trig ratios. The trig ratio for cos is x over r, so -3 over 5. And then tan is 4 over 3 because the negatives cancel each other out for quadrant 3. For quadrant 4, cos should have been +3 over 5. And then you should have had tan be -4 over 3 because the negatives no longer cancel each other out because 3 is positive in quadrant 4. Awesome. Part B. Whoa. It's worded as poorly as my stutter was. Okay, so this is worded poorly, right? They want the standard position angle, which we talked about. They're saying what are the standard position angles and to build those two triangles. To be able to figure that out, you had to figure out what your reference angle was, the little guy in the triangle. I did second tan because I used the quadrant 3 triangle to find it. If you wanted to use the quadrant 4 triangle to figure out the reference angle, you would have had to use second cos. Because those are the positive ones, for the positive ratios for those quadrants. Either way, you should have found that your reference angle was 53 degrees, this little guy in here. For the quadrant 3 triangle, standard position means you would have gone 180 plus 53 to get 233. And for the quadrant 4 triangle, you would have gone 360 minus 53 to get you 307 degrees. All right. Any questions? All right, we have 2 questions that came, I believe, both of these off of exams. So this is an old exam question. It's a numeric response question. So if you read it, says determine the 3 true statements. It usually in the question tells you how many statements you should be answering with, so that you don't think it's 1 or 2 or 4. Like it's saying there's got to be 3 true statements. Yeah. Usually it tells you that. So if you're just guessing, at least guess the right number of true statements. Place them in ascending order, the numeric response. Ascending means from smallest to biggest. That's what that means. So we have to figure out which of these statements are true. Statement 1. Reference angles must always be between 0 and 90 degrees. That is true, right? A reference angle is always between the terminal arm and the closest x-axis, which means that it is always in between 0 and 90. Question 1 is true. So that would be the first thing I put in my box. Statement 2. The angle 120 is coterminal with negative 120. If we draw that out, 120 would go here, negative 120 would go there. Coterminal means the angle gets you to the same terminal arm. Those angles did not get me to the same coterminal arm. That's 120, that's negative 120. So that means that's false. Not correct. 3. Cosine is only positive in quadrant 4. You use your Laplace law. This tells you where things are positive. Cosine can be positive in quadrant 4. However, it can also be positive in quadrant 1. And this question says only quadrant 4.
It just said is.
If it said is, then it would have been a true statement. It said only, therefore it's a false statement. Right? Those are 2 very different words and very important. Statement 4. A standard position angle of 210 has a reference angle of 30. Well, that's sketchy. 210 would go 90, 180, 210. It would be like that. The reference angle would be the measure from the terminal arm to the closest x-axis, that little green guy. You could figure that out by going 210 minus 180. The reference angle is indeed 30. So statement 4 is true. Statement 5. A reference angle is always measured to the nearest x or y axis. We never measure to y-axis, ever. So statement 5 is false. Process of elimination, 6 must be true. To prove that it's true, we say in the diagram below, cos is equal to 1 over root 2. Cos is actually equal to x over r. Looking at this guy right here, that would be 12 divided by 12 root 2. The 12s cancel out, become 1 over root 2. If you rationalize that, it becomes root 2 over 2. They didn't even rationalize, they just did 1 over root 2. But that is true. So statement 6. We prove is true. We still have one more question. Oh, I guess not. Tomorrow we'll start 6.3. We're going to have to rip through it